Hi, we're going to continue our discussion today of linearness and correlation of data by looking at perhaps some things, as you can see from the title, that summaries miss. So we're going to be investigating a little bit more the effects of influential points, is what they're called, points that may greatly affect the slope of the regression line and or its correlation. I'm pointing at this plot, which this is the average longevity of those mammals. Remember, we had them before. Average longevity of those mammals versus their maximum longevity. And so each dot represents one of the mammals that was accounted for in that table of data. We have 3 points highlighted. B is the beaver, that has an average longevity of about 5 years. However, one has been known to live 50 years, which is pretty impressive for a beaver. E is for elephant, and the average longevity of an elephant is about 35 years, but the longest lived elephant known to man was 70 years. And the H stands for hippo, where the average longevity for a hippo is longer than any of the other mammals. However, the maximum longevity is, well, let's see, this one's around 41 maybe, and maybe 52 for the maximum. So any one of those 3 points could have a significant impact, folks, on either the slope of a regression line or the value of its correlation coefficient, R. And as you think about this, which of those points do you think might be the most influential, quote unquote? To judge a point's influence, we should calculate the slope of the regression line, as well as a value for the correlation coefficient, and see what it's like with that point in, what it's like without. So you calculate the slope of the regression line and the correlation coefficient. Both with that point and without. And that way you can see how big of an influence it really does have, both with that point and without. And since we have our calculator to do those calculations quickly, it's not such a big chore to figure with and without. I'm going to just ask for your opinion here. I don't have this data set in my calculator, but I'm wondering what you think. If we take out the elephant point and leave everything else the same way, do you think that that's going to have a significant impact on the slope of the regression line? And do you think it will have a significant effect on the correlation? Will this make the correlation stronger or weaker? I'm looking for myself, okay? This is my estimate. I don't believe it's going to change the slope of that line much. It already was headed in the upward direction, and maybe it will change a little bit. It might get a little bit steeper, however, not a lot. The correlation, taking that point out, I don't think is going to have a significant effect on correlation either. Right? We already are pretty linear here. Either the beaver or the hippo would be the more influential point, in my opinion. If we took the hippopotamus point out of there, folks, imagine what happens now to the slope of the regression line. See, it had the effect of drawing that line down toward it. Without this point, the slope is going to get steeper. And without this point, what's going to happen to the correlation? Stronger or weaker, do you think? I'm figuring stronger. Without this point, it's more linear. It should get stronger. Do the same kind of analysis with the beaver point over here. If we no longer have this point, does that make a significant change to the slope of the regression line? Well, where that point was situated has the effect of drawing, again, the line toward it. However, the great majority of points were on the other side. I don't think that's going to be a significant change in slope. What about R? What about the correlation coefficient? If we remove this point, does that make the correlation stronger or weaker? I'm assuming that you're going to say stronger, and I would agree with you there. Overall, it's my belief that the hippopotamus point is the more influential. However, your opinion may be different, and the only way we could check that really is to calculate the slope of the regression line with and without that point. So we are going to see some problems that ask us to do that tomorrow. I'd like to present to you these 4 sets of data, so popular that they have a name. These are called the Anscombe data sets. And as you look at set 1, I'd ask you to think. See, we want to know what each plot looks like. So we're going to ask you to do just a little description. But I'm guessing that most of us would say that this one is fairly linear. Certainly not perfect, right? However, you can definitely see a trend, an upward trend to this data. So fairly linear, positive trend. And I don't know that I'd say it's strong. I'd say it's a moderate, perhaps, correlation. This one, there is definitely a pattern there. I mean, that is a strong pattern. However, it's not linear. So if you were going to describe the shape of this data, I'm sure that you would say it's curved. Right? It looks like a quadratic, or part of a quadratic. It does have an increasing trend, but quadratics, if what goes up must come down. So I don't know that you can say that this has a positive or negative trend, although what we're seeing of this quadratic is mostly uphill. And as far as how strong the relationship is, well, this is not linear. So talking about a value of R does not really make a whole lot of sense. Pearson's correlation coefficient, R, works with linear data, and this is not. Okay, this is definitely a curved data set. Data set 3 is very linear with this exception. We have one point up here that throws the whole thing off, right? I'm sure that most of us would say that this is linear. It is definitely increasing or positive. And as far as the strength of correlation, boy, if we could just get rid of that point, we'd say it's perfect. But that point is in there, and we can't just throw it away. So I think that you could say that it's a moderate correlation. Our last data set, look at that. All the x values are the same in this data set with this one exception, which is way to the right, higher than any of the other data points. This guy also is probably an influential point. Would you call this linear? Without that, maybe, but it does have that, so it's not really linear. Although you could probably find an equation for a line. It would have to vary a lot off of this in order to go over there and account for that point. So as we've been talking, we probably have already answered the questions here. Which plot has a point that's highly influential with both respect to the slope of the regression line and with respect to the correlation? If we remove this point, we have a true up and down line, right, which has an undefined slope. However, removing this point would make it purely undefined. As far as a regression, a correlation coefficient, if we remove this point, that line becomes totally correlated. My guess is that this is the most influential point. This one also has an effect, don't get me wrong, but this one will not change the slope nearly as much as this would. Okay? Both of them influential, this one probably more so. We'll be asking you to make some decisions like that, but let's see what the pull down has to say about this Anscombe data set. I think maybe you'll find it kind of surprising. Yeah, the slope of the regression line for each of these 4 data sets is about 1/2. The y-intercept in each of them is about 3. The R value for the first plot is around 0.8, so moderate was a pretty good estimate there. But the others aren't linear, and it doesn't really make a lot of sense to talk about R. I would kind of sort of disagree with Anscombe about this one, because I think that you could still call for a linear trend there. However, according to the person who did this research, No. Okay, they all have about the same regression equation if you think about it. The slope is 0.5 and the y-intercept is around 3, so all of them, if you were to ask the calculator to make a line, would give you the equation y equals 0.5x plus 3. At least they'd be very close to that. And they are very different looking data sets, so it's kind of interesting. We want to use the Anscombe data sets to help us look at another useful tool to decide if we have a good model, if a line is a good model for a data set. We alluded to this in the last lesson, but today we're going to focus a little bit more on making a residual plot, it's called. It's a scatter plot of the residuals, which are the prediction errors, you'll remember, for each of the y values. And folks, I have the data for the Anscombe data sets here, and we're going to make a residual plot for data set 1 to begin with. I want to get my calculator up. I have my calculator up, and I've entered the data for the 4 Anscombe plots here. In list 1, you'll notice that in plots 1, 2, and 3, they all have the same x values. The y's for each of those respective lists are in 2, 3, and 4 in my calculator, and then lists 5 and 6 contain data set 4, which is significantly different from the others. But to make a residual plot, what we need to do is find the residual for each piece of data. And what we've said is that the equation y equals 0.5x plus 3 is a fairly good model for all of them. So what we're going to do is take a look at coming up with residuals and plotting them for each point in the set. I'm going to, as I often do, set up a table because that'll help us a little bit here. I want us to think about the x values in this column, the y's in this, and we have them already in our display here, so perhaps we don't need to copy that. But what we do need to know is a predicted y for each. And we want to know the residual, or how far off each predicted y is, actual minus predicted. That's our residual. And then we'll make a data plot or a scatter plot of those residuals. Now, I'm going to have you, actually, I'm going to put my data into this table. I will catch up to you in just a minute with a complete table. As you can see, I've been busy. I have found a predicted y using this equation, and actually use my list to help me. I put that equation into list 4, and I, instead of x, typed L1 so that it would look at each of the x's in the first list and create the predicted y for that value. What I then did was, in list 5, I did a subtraction. Actual y's, which I had in list 2, minus predicted y's, which for me in this case were in list 4. And so what it did is show me how far off. Here, see, the actual y was 8.04, the predicted y was 8, and the residual, or the difference between them, is 0.04. Now in a residual plot, what we're going to do is take each of these x values and plot the x against its residual. So I have my scale set up here. Y is going from 2 to -2, because you can see that those are about as far away as we need to get. The x's in this data set ranged from, well, I went from 0 to 15. My highest x value is a 14. It's going to take me just a second to plot these. Let's do the first one together, and then I would recommend that you shut it off and finish on your own there. But 10 and 0.04. So that's a positive residual for the x value 10. 8 goes with -0.05, so here's 8, and we're 0.05. Really hard to plot that. That's so small. 13 is -1.92. That is down here a bit. And I'm going to ask you to continue on. You want to plot each x against its residual, and then I'll catch up with you in a minute. Okay, here's my residual plot. As you can see, I have one dot for each of our data values x. The The y value is the residual, the prediction error. And what we're looking for in a residual plot is a lack of a pattern, folks. We want to look at if a line is a good fit for a data set, the residual plot should look very random. You shouldn't see any distinct patterns of increase. You shouldn't see things getting farther away the farther you get out. You should not see any kind of a pattern, and this one looks pretty good. Okay, let's try that again, only this time I'd love to show you how your calculator can do the work for you. So instead of building this table, I'm going to just do it this time in my calculator list and ask you to follow along. For the second data set, I have that X's are in my list 1, the Y's for that data set are in my list 2, and we're going to create and sketch the residual plot. We'll show you how to do this using your calculator, and so I'm not going to write a big table of values here. I am, though, going to remind you of what we have to do. Okay, to make a residual plot, we need to know the prediction error. So we need to, in list 3, enter the regression equation using L1 in place of X, because that's where our X values are. In this example, you'll recall each of those data sets had just about the same regression equation, and it was y equals 0.5x plus 3. So I'm going to, in my list 3 up on the title, I'm going to put in 0.5 times list 1, okay, that's where our x's are, plus 3, and that'll give us a predicted y for each of our x values. So predicted y's are in list 3, and I'm going to put that right here, predicted y. Alright, to find the residual, that's the difference between actual y and predicted. So in list 4, on the title, I'm going to tell it, take L2, actual y, minus L3, predicted y. List 4, this is what we're doing. We told it to take L2 minus L3, and if you think about that, it was actual y minus predicted y. That's your residual, folks. For each x value, you now have a residual that's here in list 4. Now, I sketched that last residual plot by hand, but there's no need for me to do that. My calculator can make a plot that is, so I'm going to create a scatter plot. That versus list 1, the x values, against their residuals. Okay, so I'm going to go ahead and get into my plot settings, second and y equal. I need to change plot 1 so that it's looking not at list 1 and 2, but at list 1 and 4, because that's where my residual. I'm going to cheat and use the zoom stat window. That's zoom and 9, and what that does is, oh my. Hey, if this is our residual plot, folks, we have a problem here. Here comes my sketch, by the way, because I am seeing totally a pattern here. Yeah, this is not good. If our data set is producing something that is totally visual pattern, then a line is not a good representation for that data set. Now, we got something that looks just like a quadratic, but I'll just remind you, this data set did have that quadratic shape to it. So when you fit a line to it, points are going to be under and over that line, but going in a patterned way. That's exactly what we saw there. So you could definitely say that a line is not a good fit for data set 2. since the residual plot shows a strong pattern. All right. Just to go back in time just a little bit, and what we've said from the very beginning is that if you look at the original scatter plot and you see a cloud of points that is elliptical or oval in shape, that would mean that a line is a good model. If that's the truth, then the residual plot will look totally random. Okay, you shouldn't see any discernible pattern. If a line is a good fit, the residual plot should be random. Okay, you shouldn't see any kind of discernible pattern. Alright, so I hope we've given you something to think about here. In class tomorrow we'll have a chance to work on some problems where we create and interpret residual plots. So get out there, try the U-Try, and we'll catch you in class. Bye-bye.